Good evening, everyone, and thanks for joining the NYJavaSIG meeting. Very happy to have you with us tonight. So today we are having this meeting from the Bank of New York Mellon. I'm working here. My colleague Chandra works here as well. I have more colleagues from Bank of New York Mellon. So thanks for the Bank of New York Mellon for giving us the space, sponsoring the food. And thank you for my CEO, Sartak, who provided everything to us. So thanks for him for the space. Just a couple of things about BNY Mellon. I know many people doesn't know BNY Mellon. Unless you work on the finance, you don't know much about the Bank of New York Mellon. It's the oldest bank in the US, and we are pretty much a technology company. So we have 3 Java champions as part of Bank of New York Mellon, myself, Chandra, and Don, which might visit us later today. We also very in touch with the community. So we have leaders from the New York JavaSIG, myself and Chandra. We have leaders from the Garden State Jug. Chandra is one of them. And we have leaders from the Pittsburgh. Sirisha is one of the leaders from the Pittsburgh. We also have open source. We contribute to open source. If you go to GitHub repository, we have katas that will teach you about Spring, collections, Eclipse collection, Spring Boot, so everyone is free to collaborate. Last thing, we're also part of the Open JDK outreach program. So every time there's a new version of Java available, BNY is part of this program and is going to test everything to see if things are working fine and everything's working as expected. Before starting the event, I just wanted to give a word to my friend Chandra. He has a few words to say. Thank you. I hope you enjoy.
Thank you, Rodrigo. Hello, everyone. Hopefully some of you here know me, and those of you who don't, lucky you. So I'm here not as a jug leader for New York JavaSIG and neither for Garden State Java User Group. I'm here as a representative for DevNexus, the technology conference that happens in Atlanta every year. And this year, they were looking at what was the best presentation that happened at DevNexus. And it so turns out that our very own Frank Greco won that award. I'm here to present that award to Frank. So Frank, if you don't mind stepping over. Oh, there you go.
Where's your award? Somebody stole it already?
It's here, man.
So the award was there, it was gone. Frank, if you don't mind stepping over.
Oh, thank you.
Congratulations.
Thank you very much. Thank you. Thank you, people of the future. Thank you. Thanks. That was a lot of fun. That was my ML and ChatGPT with Java talk. So that was cool. I think if you were here last month, you saw the beta test of the presentation. So that was great. So so thanks for again, thanks to the Bank of New York Mellon for hosting us. Happy April. This is our April meeting. Next month we have quantum computing in Java. So that's going to be very interesting. So let me introduce Peter. So Peter is a Java champion, and he's well known for being one of the super experts on the planet in high performance and low latency Java. And you were here like about four plus years ago, giving a talk. So Peter's known internationally as like a top expert in the field. So without further ado, Peter Lawrey.
Well, thank you, Frank, for organizing this, and thank you for BN Mellon for hosting it. Let me just share screen. Yeah, so today's primary focus is going to be on shedding a light on the hidden cost of allocations and some of the consequences in fintech type applications where you're really focusing on low latency and also vertical scalability. So Chronicle Software was founded by myself 10 years ago now. Initially as a consulting company, but now we're much more focused on providing supporting software. Wow, another 10 pizzas have just arrived.
You can't have any pizza less.
Okay, so yeah, so at the heart of all of our products is low latency durable messaging, which is an open source product called Chronicle Q. We also have distributed messaging in other languages such as Python, Rust, C++. We have a fixed engine, which is nearly half of all of our revenue comes from fixed engine licenses. We have an EFX trading system, which is used to run a number of FX in a number of banks. We have a matching engine, which is fairly recent. It's got a lot of interest. And this year we're looking to produce a Rust version as well as a Java version. And we have an OS tuning tool, which is becoming increasingly popular because it's very easy to just install and use it to reduce jitter within the system. And certainly for our own purposes, we use this for all of our benchmarks because it'll help reduce the higher percentile latencies. So one of the things we'll talk about today is the hidden cost of allocations. Now, the reason why this is a hidden cost is that generally the focus is on the GC pause time. So that's something that JVM will tell you. It reports it as it happens. And there's often an assumption that if your GC pause time is low enough, then you don't need to worry about allocations. Another assumption is that the cost of allocation is very small, and generally speaking, it is. But as you'll see in a moment, that depends on whether you're using the whole machine or not. If you're trying to use the whole machine, and a lot of machines these days have quite a lot of cores, then that cost increases dramatically. So this is based on a benchmark, which is open source, but all I'm doing here is having different number of threads, creating objects as quickly as possible, and I'm timing how long it takes to allocate those objects. And as you can see, for a small number of threads, depending on the use case, it's between 4 and 6, the number of the time it takes to allocate these objects is pretty low. And certainly for small objects, which I tend to use in benchmarks, 44-byte objects, quite small, that the number of threads you're using doesn't really matter. You can have more and more threads, and it doesn't take any longer. Although for larger objects like 640-byte in this case, you actually start to see an increase in time to do the allocation almost immediately. Certainly above 2 threads does it go up. Now, the reason this is significant is that if you're using virtual machines, for example, there is no protection from this. So if you've got one virtual machine on one JVM running in a virtual machine on a piece of hardware, then that can consume the memory bandwidth of your system, even though you've got other virtual machines trying to use the system as well. And so this is running on a reasonably high-end system, 5950X, which has very high bandwidth in itself. But it gets worse as you try and use more and more threads. Essentially, what happens is that as you try and go beyond about 4 threads, the time it takes to allocate each object just goes up linearly. And the reason for that is that you're essentially saturating how much allocation in terms of gigabytes per second that system can sustain. If you have slightly larger objects, you can achieve higher throughputs in terms of just gigabytes per second, but it doesn't make a lot of difference. There's only a factor of 2 here, even though the objects are more than about 15 times bigger. So what happens is you reach a threshold as to how much your system can allocate, and then adding more threads at this point doesn't make any difference to the throughput of your system. So even if you're not worried about low latency, but you do care about throughput, then allocation rate can still be penalizing you. So to put this in another form, you can see here that if I go from 2 to 3 to 4 threads, allocating objects, in this case, it's just like mad, essentially. The time it takes to allocate each object is quite small, right? 15, 18 nanoseconds. Why worry about that? And that's the general message, that allocations are cheap. They don't really impact us. It's not a problem. But when you go beyond 4 threads, going beyond using 4 cores out of your 16 core system, it starts to ramp up because you've hit a bandwidth limitation. And so that's where your allocations can be restricting how much throughput your server will be able to do. And it pretty much goes up linearly. Now, the reason this number is significant is I have another benchmark, which is more realistic, that this 150 nanoseconds pops up again, which I've highlighted there. Also, I ran the benchmark with 2 JVMs. So splitting the JVMs into 2, so like the 5950 doesn't have NUMA regions, but it does have 2 dies internally. The cost of talking between those 2 dies is not the same as talking between cores in the same die internally. So what I did is I created 2 JVMs. Each one was locked to the individual dies, just to see whether there's some sort of NUMA-like overhead. And actually, after all that work, you got pretty much the same result in terms of number of objects per second I could create. So it's not that. So this is a slightly more realistic example. So what's happening here is that using Chronicle channels, which is open source, it's in Chronicle Wire. I've got a TCP client. It's sending a message to a server. The echo server, all it's doing is copying that object, it's just passing that object back again. So it's an echo service. It's a fairly standard benchmark for getting round trip times. It keeps it really simple. So this is how we structure our microservices. So we've got an interface that we work to that defines all the messages that can come into the system. We have another interface which defines all the messages that can go out. And in this case, I've got the option to basically trigger it to create one object. So when we deserialize objects, we use mutable objects because they're recycled. So every time we deserialize an object that came off the wire or came off of Chronicle Q, from any other source, we keep reusing that object. So that object is implicitly reused. There's no allocation going on. So we can process messages and send messages out where end-to-end there are no objects being created at all. But what is the impact of if we just created one object? How much difference would that make? And this object's quite small, so why worry? So this is what it looks like in our unit tests. In our unit tests, they're data-driven tests. So we use YAML for input. Obviously, the input and the output in this case is the same. So one of the tricks we use is that we do actually make use of comments. So comment in the input is bled through to the output. So when you look at the output, you can see some sort of correlation between your comments and what was produced. And this is the difference that it makes. Also, you can see there's a difference between different versions of JVMs as well. So in particular, Java 11 outperformed Java 8 for this benchmark. It doesn't in all of our benchmarks, but in this one it did. And we're getting about a good number of events per second. We've got about 60, around 65 or so million events per second being processed via this mechanism. And that's about 4 billion a minute. So it's a very good throughput you can achieve out of a single machine. This machine is acting as both the producer and consumer. So it's having to do all of the work of the client and the server. So a server standalone would potentially do better, although at this point you're pretty much saturating most available TCP connections. So you would have to have a very good line to be even to throw that much bandwidth at the system. But one of the things you'll notice is that there's a discrepancy between the throughput and average latency with no objects versus one object. And the difference is approximately a little bit over 150 nanoseconds. So at this point where I'm using all the threads in the machine, that's the 32 thread example from the previous benchmark. So you can see in a slightly more realistic benchmark, previous one, all it was doing is creating objects. This one is still not really doing very much, but you can see that number pops up again. You're getting about 150 nanoseconds added to the average latency of each request due to that one object being created for each event. And the significance of this being that if you were to look at the GC pause times, it's only spending about 0.3% of the time GC pausing. And the reason is that obviously in this example, we have a lot of very short-lived objects. Cleaning up large numbers of short-lived objects is extremely cheap because it's not copying pretty much any of them, and it's just then blasting the whole memory. So the GC time looks really good. However, the time it takes to allocate it is sucking about 25% of our throughput. So it's not 0.3% the cost, it's actually 25% is the cost. It's about 80 times what the GC is reporting. Because there is a cost in allocating very short-lived objects, there is a very little cost in cleaning them up. So is there kind of any rule of thumb to give you, if you, rather than go through all of this analysis, is there a simple way to figure out whether allocations is hurting my system in terms of throughput? And that is to look at the amount of bandwidth different systems can handle. So a typical server, you might be able to handle about 10 gigabytes per second. Some can do higher. Depends on your use case. Certainly, like I said, larger objects, you can get a bit more, maybe 15 or even 20 if you're consistently using larger objects. But there'll be a flatline threshold that all the JVMs combined on your server, if you add up all their allocations together, you may find that that number doesn't actually fluctuate as much as you might imagine. And that suggests you're hitting some upper limit. And that's the point at which you can say, well, if I reduce allocations, I will improve the throughput, not just of that JVM or that process, but perhaps the entire machine. The alternative is, of course, is to split those JVMs across more machines, which might be easier than refactoring the code. But you can see that you're hitting some upper limit that's not to do with exhausting the number of CPUs or even the amount of memory you've got, but just the memory bandwidth between the CPU and the ability to allocate. And I've actually come across this number once during consulting where the JVM was sitting very comfortably at 10 gigabytes a second pretty much all the time. We reduced the allocation rate by 30% and it stayed at 10 gigabytes per second. The throughput went up by 30%, but the allocation rate was still the same. It was only when we reduced the allocation rate by 40% did we actually start to see a drop in the allocations, because that was no longer the constraining factor. So, so let's start looking at a little bit of code and some examples of what we do. So we model each service as using Kappa architecture, and I've got more diagrams for that coming up, but the way we model all the inputs and outputs is to have a Java interface. So this is fairly Java-centric in terms of the way you're designing your application. But by having an interface, the nice thing is you've got a compile time check that the outputs of one microservice leads to another, and you can, when you're refactoring, you can ensure that they're sending the same compatible messages, that your downstream microservices are handling what your upstream microservices are producing, and it does it in a fairly transparent way. So we've got a very simple service here. It's simpler than the previous example where it gets a message in, which is say some string, and all it does is add an exclamation mark. So when we come to testing it, it is fairly straightforward. We have YAML for the input, we have YAML for the output, and it's very easy to see the difference if there's some sort of inconsistency, because it's a multi-line text comparison at the end of the day. And so in IntelliJ, for example, you can immediately see where the discrepancies are. Now, in a more realistic example, I seem to have the slides messed up, but I'll come back to that. Okay, so so one of the things that comes up is, well, how do we model sending any kind of guarantee about message delivery or syncing? What we can do is, obviously there are many options in terms of using a database, but what's a really lightweight way of doing it is we add a message which it recognizes So this is an interface we support and recognize, where if you call the method sync, the underlying infrastructure will perform a sync at that point. You can control whether it's an async or a full sync to disk. It will work across TCP connections as well, and all along the line it will do a sync as configured by whatever stage it's up to. The nice thing about that is the reader knows at what point syncs were performed, and it does it asynchronously. So from the writer's point of view, it can say, all right, now I need to sync. The writer doesn't wait for that sync, only the reader waits for the sync by default. You can force the writer to sync as well, to wait for that sync, but generally the writers don't do that because they want to have the lowest latency. But if you need some sort of guarantee at a certain point that it was synced, you can make it that the reader doesn't perform that operation until it's seen that that's happened. So you can model this in a number of different ways. You can have sync can mean that you need to have an acknowledged replication, or that you're waiting for disk, or you're waiting for an async from the OS. And this can make a difference to latencies involved. So this can be the highest, having durability guarantees is sometimes the highest latency impact in a system. So for example, in payment systems, they often have that requirement that something has to have gone to a database or it has to have been synced. So this can make be the most important thing to make sure that it's no more complicated than necessary to get the best performance. Now with SSDs, the sort of sync delay you get, so on the blue line is where you've got the strongest guarantee. Every message has to be synced to disk. However, the black line is if you only ever async. So that's more of a hint to the operating system. You're not really waiting for it, but you will trigger the operating system to flush the data out. There is some benefit in making this programmable because you can do it based on business risk rather than based on some sort of technical metric. So a common way of doing it is say, well, if you've got more than 1,000 messages or more than 100 megabytes, then sync periodically. So I never lose more than 100 megabytes. That doesn't necessarily mean much to the business. They want to know, well, how much money could I lose, right? So you can make it that heartbeats are never synced, no matter how many there are. Small trades or messages going backwards. But if you get an order for 10 million, just that one alone, I want to sync it, right? So you've got that kind of control just by where you decide to call sync. And that can make a huge difference, particularly for the typical latencies. For the tail latencies, it can help because they're the worst case. That's where you actually are syncing. But for the majority of messages, you can end up improving the throughput and latency by having that kind of control. So a lot of banks still use SSDs because they're more traditional disk and there's a lot more confidence around them. But in the future, we'll be shifting more towards NVMe because they're a lot faster. They still have higher tails, so they're not necessarily a lot better than the SSDs, but in terms of typical latencies, you can see that this was on the same system, by the way, doing exactly the same benchmark. So the typical latencies for an SSD, about 7 milliseconds when you're syncing, and on the same system, it dropped to about 1.7 milliseconds. And again, you get an even better profile if you're not syncing absolutely every message. And then if you, this is where you're only waiting for replicas to acknowledge the message. You're not actually writing anything to disk. You can get even lower latencies again. So this is closer to what a lot of the clients do for trading systems. They'll either write the message, which is the very bottom one, which is basically if every JVM dies, it will still get written to disk, but the OS and the disk have to keep running. That's often the sort of guarantee that a lot of our clients actually take. They say, well, that's a risk we're willing to bear, but if the JVM dies, we still won't lose that message. But some of them, which need a higher guarantee, they will just wait for an acknowledgement via TCP. So it's not actually gone to any physical disk, but if the entire machine is lost, there's at least a replica on another machine. So a more realistic example is to do something like new order singles, and you chain these services together. But again, it's still an interface defining what messages are expected. The message type maps one-to-one with a method name. And so we do a couple of tricks to make those DTOs much more compact. We use character encoding for both short strings and for timestamps. So we standardized a few years ago on using nanosecond timestamps everywhere for all our systems. So we've got a clock in Java, written for Java, that produces nanosecond, sometimes 100 microsecond resolution times in reality. And we also use base 85. Base 85 allows you to put up to 10 characters into a long. So that gives you, and as there's 85 most common ASCII characters, that gives you quite a bit of flexibility, and you're not actually using strings at this point, which is like there's no object allocations, no indirection. You can copy it as it's just a long comparison. And internally, you don't need to know what those characters are. It's often an ID from the computer's point of view. So it's not actually buying you anything, making it as a string. And then obviously the framework, this is again in Chronicle Wire open source. It will implicitly, when it's going to YAML or text or JSON, it will implicitly do the conversion backwards and forwards for you. But you may also have some strings like client order ID that uses object pooling by default. So for as good as that gets, so client order IDs tend to be random, but they do generally happen 2 to 3 times. So there is still some benefit, even though you've got no control over the format or the content of the client order IDs. But so for example, you might send an order and then it might get canceled or adjusted. That client ID now has appeared 2, maybe 3 times over its entire life cycle. So you get a little bit of benefit there. And so this is what a unit test might look like. You have YAML in. This is a new order single being generated, created for the input, and then you have the expected output that this produces. So you can see here it's only got microsecond timestamps, but it's still human readable. It's the important thing, even though that's being just stored as a long inside Java. And that reduces, again, the number of objects being created, but also just how many are being managed. So again, if we break this test in a way, how easy is it to see what the problem is? Well, you can see pretty quickly that the order ID is incorrect. So one of the things we do is we use timestamps for IDs. And there's a couple of reasons for doing that. Is that we can, we have support for generating IDs where the bottom 2 digits are the host ID, so you can have up to 100 machines with pre-allocated numbers, and all the top digits are the nanosecond timestamp, well, with a resolution of 100 microseconds. The benefit of that is that you can then have unique IDs across a cluster of servers without any coordination between them, and it's extremely cheap. It takes about 32 nanoseconds to create one of these timestamps. And then that becomes just a long. So it's a unique monotonically increasing time ID, which has got the time built into it. So you know when it was created, you know which host it was created on. And in terms of readability, it's just a time of day. So it's a readable ID as well. So there's a lot of cross benefits in having that unique generated timestamp across multiple machines. If you want to know more about that, I have some articles on my blog on that topic. And again, it's open source, so you can read all the code. So reducing object allocation is all tied in with reducing accidental complexity. And this is why testing is actually really important, because by having good tests which clearly define what's actually required, particularly what's required by the business, makes it really clear that if it's doing more than that, you don't need it, you can remove it. So anything that solves that problem of completing every test but with less work is an improvement. So it might not be quite obvious that actually having a good test suite helps you improve performance, because you get really focused on what is the minimum I actually have to do to satisfy all my requirements, rather than let's put lots of components together until the whole thing works. And one of the things we find increasingly useful is generated regression tests. So that's often not talked about very much, but the benefit of generated regression tests is that, unlike the first four on this list, you require domain expertise. So one of the big challenges of test-driven development or behavior-driven development is that even though notionally you start with that, you can on a project level start with test-driven development, but in terms of your career and your understanding, you can't. Because if you don't have expertise, you can't create those tests in the first place, right? So in terms of in terms of your career, you will be you've worked on those projects before, and you're using that experience to create tests, right? So that means that in reality, from your perspective, you started with an implementation. You learned from that implementation. Then you created tests in the next project, and then you were able to start with this test. But if you haven't started, you don't have that expertise already, which is kind of hidden, it's very hard to start with those tests from the beginning. So one of the challenges of a lot of this test-driven development is that you don't necessarily have expertise in all the aspects that are needed to develop that application. You will have expertise. It's really good to codify that right from the start, but there's a lot of areas where either they're not particularly important or they're just outside your expertise. So you can't create those tests from the start. You can only discover them as the project goes on. And that's where regression testing is really useful for where you discover, well, I've created an implementation that satisfies everything I do know. How does it behave for all the things that I haven't thought about? And so we've got a tool built into the open source for generating regression tests. So you saw before they got YAML tests, and in this case, it's a book builder for our EFX trading system. There's 57 tests for it, which were suitable for using this kind of generation. From that, we generated all sorts of combinations of tests, and so the 57 is largely happy path, right? So 57, in this sequence of events, it produces these correct results. But what about all the unhappy paths, like bad data, fields missing, duplicate messages, messages in the wrong order? You can do all of those manually, but it's extremely tedious to maintain, because for every time you change something in the happy path, like add a new field or add a new message type, you're going to have to maintain all the variations where you've lost things. So it makes much more sense to make all that tedious work completely generated. The downside is that generating the test can result in just too many, because there's so many combinations you could explore that could potentially cause a problem. So what we do is we have a technique for filtering the tests. The default behavior is quite simple. It looks to see whether does it produce a message that no other test produces. So if it produces a new message that no other test produces, it's retained. And in this case, it increases our code coverage by about 3%. But that's deceptively small, because actually in doing this integration, we found all sorts of problems we ended up fixing, which doesn't really show in this. And at multiple levels, actually, we found issues. So this is after we sorted out all the issues. It still showed up as increasing the code coverage. There are other tests as well. So this is not the full code coverage of the application, but this is just the code coverage delivered by these easily manipulated tests. And then the number becomes more practical. So we get 426 tests. It takes about 34 seconds to run them all. And note, because our services are so lightweight, in every one of these tests, the service is starting up from scratch. It's being fed all its reference information. It's being run through all of the messages that are associated with it. It's being checked and then shut down. So it's running through a test in about 1/10 of a second to do all of that end to end. And again, so some of the benefits of having really lightweight microservices that are low latency is that you can run through lots of tests, starting up and shut them down because they're all so lightweight, that this improves the development cycle as well. So your iterative development goes faster. It's not just a benefit in production for some trader, it's actually a benefit for the developer to have the ability to just run through lots of these services that are really lightweight, very simple, and it improves your productivity as well. I'm not sure I was going for time. So a related factor to this is vertical scalability. So one of the things that makes trading systems and order processing different is that order matters. So this reduces your ability to parallelize or horizontally scale your application, because you can't just process them all completely independently. There is an extent that you can do that, and that's usually done by gateways such as validation, checking that this is a real authentication, all of that sort of stuff. That can be horizontally scaled, but there's a certain amount of work that has to be done by some sort of centralized service. And suddenly trading securities, what tends to happen is even if you've got a large number of symbols or a large number of instruments, during your peak times, a very small number of instruments will have most of the volume. Fixed income is one of the worst for this. For example, in London fixed income, the 3-month short has 90% of all trading of all fixed income products in London. So that one symbol could be standalone, but then every other symbol combined doesn't actually compare with that one symbol. In FX, it tends to be something like euro-dollar. So euro-dollar can have a very large percentage of activity for all of the possible currency pairs. And the reason that's significant is that is your bottleneck. That's what you have to tune for. If you can handle euro-dollar, you can handle every other symbol. So, so once you get, you find the key symbol, your busiest time of the week, so equities that might be non-farm payroll, you need to be able to cope for that situation, and then the rest of the week, all the other periods will be covered in terms of being able to handle the throughput. So this is where vertical scalability becomes key. So, so it becomes a functional requirement. So that's another key difference, is that if it can't perform, then it fails to meet its functional requirements, not just, oh, it'd be nice if it went faster, oh, it would save us some money if we use less servers. Those are all great, but if it doesn't actually perform, particularly in hedge funds where your trading is optional. So if you're at a bank, you're providing a guaranteed service, you have to trade. It's not optional. But in a lot of hedge funds, whether you trade or not is entirely down to you. So if you're not making money, you shouldn't be trading, right? So failing to trade is possibly less expensive than trading incorrectly and slowly, because you will lose more money trading incorrectly than you will just not trading at all. So so performance can be very key to whether you can whether you should even be running or not. So what sort of latency criteria we're looking for? We're looking for to be able to have microservices that have latencies of between, say, 1 and 10 microseconds. So that's end to end, including transport, and throughputs of between 100 and 1 million events per second, right? And so at this point, if you can get that kind of vertical scalability, often questions about horizontal scalability aren't even a problem, because that may be far more than you ever actually have. So there's no actual need to have more machines to deliver the performance you need. Now, one of the things that can be surprising is how much accidental complexity some systems can have, right? You might think that, oh, well, it's tens of percent slower than it could be. And when you have an existing system and you try and tune it, it's not always obvious how you can improve it by, say, 10% improvement. But if you were told, well, I need to make this 10 times faster, you go, well, I'm not sure where to start with that. And that's where reducing accidental complexity really helps in if you need to get an order of magnitude improvement. I had one client in London. They had basically had some money at the end of the calendar year, and they said, well, we can hire you for a month, and we need to improve our outliers. We want to have a 10 times improvement in our outliers, but we can't change the software or the hardware. Which and initially they said, we want you to guarantee how much improvement you'll make. And I said, well, I'm not going to take it that far. But interestingly enough, it came down to analysis. Once we analyzed, well, what was it spending its time doing? It turned out someone had already written the solution for each of the problems we found. It's just that they couldn't convince anyone to use it. So in many cases, some of the solutions had been written 3 years prior by a contractor and had never been used. And it came down purely to configuration, turning on some of the solutions other people had already written. And we managed to reduce the 3 nines by a factor of 25, just from configuration changes. So I initially assumed, well, we have to write some new code, but it turned out someone had already written the code and just needed to have the analysis there to show that this is what the changes need. So having good analysis really does make a huge difference to being able to see, well, what do I really need to change to fix this? So this is from a benchmark that I did. Again, this is just an echo service. I'm sending a message to Kafka. Kafka's it's going to a microservice. The microservice, all it's doing is sending it back again. There's only one microservice in this case, unlike the previous one where there were 16 microservices. I'm just trying to keep it really simple. And the delay involved wasn't very large in the sense that you couldn't see it. Human can only can't see delays of about 40 milliseconds. For context, older movies used to be around 24 hertz, 24 frames a second. That wasn't obviously a problem for most people, right? You didn't visually see, oh, well, if the frame's changing, oh no, here's another frame. That was entirely smooth and to you. And that's about 40 milliseconds per frame. So this latency looks really small. It's only 2.6 milliseconds, right? So appreciating really short delays that you can't even see can be hard to communicate to people why that is actually quite a big number. So one of the techniques we use is to translate it into distance, like how far could I send a signal in that amount of time? So in 2.6 milliseconds, you can send a message from New Haven down to Washington, which is a fairly long distance through copper or fiber, which is about 2/3 of the speed of light in a vacuum, by the way. They're about the same, which is why microwave links are popular in trading, because the speed of light through air is quite a lot faster. It's only slightly slower than in a vacuum. So so you can go faster than the speed of light in a fiber by going through the speed of light in air. But anyway, so a very short delay that's too small to see, but you translate it as a distance becomes obvious. Also, during this benchmark, you can see a pattern which people are quite familiar with of a lot of GCs. This is quite a bit of sawtoothing going on here. This is only the client. So this is not all the objects being created. This is just the objects being created by the client in this case, not the broker or the service. But there's a lot of garbage being created. Interestingly enough, you'll notice that it looks like the maximum is sitting at around 13 gigabytes per second, but it's not. For some reason, they make these bars 2 seconds. So it's actually 13 gigabytes every 2 seconds. But like I said, it's not the only JVM running on this system, so it sort of matches my previous estimate. But it's quite a high allocation rate. And you can see the biggest allocation is byte arrays, which is not uncommon for messaging systems, because what they'll do is they'll expect a byte array and they'll give you a byte array. And every time that's a different byte array object. So every message has to translate to at least one allocation at each end, which is quite painful. So, so by comparison, doing exactly the same thing using Chronicle Q, which is open source, as I mentioned, it's a much shorter distance. So again, it's a delay you can't see, but it's actually is single-digit microseconds. And that's a much shorter distance. It's about the time it takes to send a signal across the battery. But also what's interesting is the GC profile. Now, most of the garbage here is because I used Java 8. Java 8, the flight recorder, did produce a little bit of garbage. Java 17 doesn't have this problem. But in any case, it's actually lying to you, because at the top you can see it's creating objects, not very many, and at the bottom the memory usage is 0 because it's tried to take out all the objects it's adding and then it removes and hides those from you. In any case, even there the allocation rate is about 600 kilobytes every 2 seconds compared to 13 gigabytes every 2 seconds. So there's a remarkable difference, and most of that is actually the profile. So this is doing, actually this is not even doing the same work. So in the Chronicle Q example, for whatever reason, I just, maybe to show off, I don't know, it's actually doing 5 times the throughput as well. So again, it's hard to represent the difference between this. So this is a logarithmic scale on both axes. So on the left axis, it's the latency in microseconds. And on the right-hand side is the percentile. So a percentile is take all the timings, sort them. The 50th percentile is the one in the middle. The 99th percentile is the 99% from the start, or the worst 1%, worst 1 in 100 sometimes. Generally, we look at 3 nines and 4 nines in Java. 3 nines is fairly common for our clients in terms of a number that they would like to look at. I still think it's worth looking at the 99th percentile. And one of my things I advise is if you can't get support for improving your system, start reporting the 99th percentile instead of the typical. And that will be a much bigger number and it will sound worse. Then you're more likely to get approval to improve the performance of your system. Interestingly enough, the ratio of the delays is surprisingly consistent across different percentiles. It's a factor of about 750 times. Now, the important point is, as I mentioned, it's doing the same work for that particular benchmark. So the other 750 times delay compared to it is entirely accidental. It's not essential because, well, Chronicle Q can do it. And even Chronicle Q isn't as efficient as it could be in theory. It's just, that just happens to be the implementation. So a very large percentage of everything that it's doing, and by the way, Kafka is one of its selling points is low latency, by the way. So it's not a bad tool in itself, very widely used. So it's not a poor choice. It's just that even in that case, there's a couple of orders of magnitude of accidental complexity in terms of impact on latency. So as I mentioned, a rule of thumb, so how can you get to that kind of level of accidental complexity? Well, applications tend to have multiple layers, and each layer usually adds a little bit of abstraction, which adds a little bit of overhead. But if you have like 10 layers, and each layer is adding about it's 50% abstraction, 50% of actual work, then scale that up, you end up with about 1,000 times overhead compared to the actual work being done. So I think I'm getting on for time, so I'll go through the rest of it quite quickly. So in summary, we use Kappa architecture. The most essential functions are normalizing functions for gateways, So it's just the latest message. You translate it into some other message, change the format, normalize it, or denormalize it for the purpose of the external system. Most of the more interesting bits are somewhat stateful, which isn't technically a function, unless you say, well, actually, it's a function of every message it's ever seen. So that's one of the key differences, is that all information is an event. Every piece of reference information, configuration, everything's an event, is fed in as an event. So then it's just a replay of all those events to recreate the state at any point. It also means downstream, you can replay the state at any point. You're not having to deliver massive snapshots out. If anything that the downstream system component needs to know can be recreated from there, which importantly means that you log basically nothing, right? So we will log things on startup because it's quite useful to see there's a health check, you can see what it's doing. But once it's up and running, if it's not producing critical errors that can't be written to the queue, then there's no logging at all. So logging just disappears entirely because loggings are often a very large source of garbage and delays. It can be up to 30% of your system delay can be just in logging. So we don't log anything. Everything's an output to a queue, right? And you can then see whether some message failed or whatever based on reading that queue. So you can combine these together to chain them, but they can all be tested completely standalone. So the control system in the middle, all you need is its inputs, and you can recreate its state. So things like HA become much simpler. Basically, you reproduce the input messages on the HA system, you replay it with the same code up to the same point, it will be in exactly the same state. In more complicated systems, we can do live upgrades. So the other components don't have to be running the same version of the software. So you can have two versions of software running at the same time, watching what each is doing, and you can switch across which is the primary, which makes all the decisions, and you can switch back again if you have regret about the upgrade. Like so one of the common things happens is if you don't like the behavior of the new configuration in terms of how it's trading, you can revert it back live while the system's running. That's particularly critical in crypto space, where they want to have 24/7, Christmas, New Year's Day, Easter. They want to be running all around the world all the time. So what sort of latencies do you get? So we have matching engine, as I mentioned, but it shows an example of so previously they're all benchmarks. So obviously the microservice is as trivial as possible. This is an actual microservice that does something useful, which is as a matching engine. So the time it takes a new order single to produce a fill, an Acumen fill, is typically around 1.3 microseconds. And the 3 nines being around 3 microseconds. So this is on a 5.950x. 7.950x is about 30% faster than that. But this is really just an example of what a low latency microservice should do in terms of performance. Now, obviously, if you're going to put in a gateway so that it can connect via TCP, again, a typical gateway might be a fixed gateway, which is in this case our fixed gateway, but there are other protocols you might have like JSON or whatever. So that adds a latency. So the typical latency is around 5.5 microseconds, and the 2 nines is under 10 microseconds. So that's a sort of not an unusual use case. We have a client that about 4 years ago now, they were getting the 3 nines wire to wire under 20 microseconds, going through 3 microservices within the system. Like I said, we're looking to increase our support for Rust. We're seeing more and more use of it. And this matching engine will be probably converted to Rust by Q3. So there's a comparison between languages now. So you can see that Java, even though Java, it performs very well for most use cases, there are alternatives, of course, that are even smoother if you look at the high percentiles. Now, the interesting thing here is that the typical latencies for Java are very good, and in the 90th percentile as well, even in this use case. The 3 nines is still within just a couple of microseconds. However, if you use the C++ version or Rust, you get much flatter latencies. And previously, I only put 4 nines because after the 4 nines, you tend to get a figure that's very hard to reproduce, even between runs in Java. Certainly, if you care about more than 4 nines or higher, then some other language like Rust or C++, that's the point where it really does make a big difference, your choice of language. But up to 3 nines, one of the benefits of Java is just greater availability of developers, right? Access to resource, time to market, and you're much more likely to see a good balance between business knowledge and developer ability, which is very hard to find in a C++ person. If you can find a C++ person that also has really good business knowledge, they're probably paid very, very well. And that's the end. So hopefully we've got some time for questions.
Questions?
Any questions?
Hi, thank you. You had all those at the beginning of your talk. You had all those graphs about allocation and performance.
Sure.
Did you do any testing on 32-bit Javas?
So the question was, in the first section, did I test 32-bit JVMs? I tested a 32-bit JVM. I don't have the numbers there, but I did test a 32-bit JVM on the same machine, and there wasn't a remarkable difference. What I would have liked to see for comparison we also test on Raspberry Pis, for example, to make sure we've got lowest common denominator, and that then there's so many differences in the architecture that it's hard to then make a lot of comparison.
My experience is I was able to cut my cloud server cost in half by switching from 64 to 32.
Yeah, that could be possible, particularly because 32-bit JVMs have a lower overhead for the object headers, for example.
The overhead is, I'm a little surprised if the overhead that you're talking about is just access to memory, which is basically what you were saying at the beginning of your talk.
Yeah, the key thing is that 64-bit JVMs have actually used 32-bit references in reality by default up to 32-bit gig heap. So
I just cut my memory. All I did was change from 64 to 32 and cut my memory usage.
Yeah, I think that's definitely worth trying for certain use cases. Although in our case, we tend to always use 64-bit. Because in reality, most of our memory usage is entirely off heap. Chronicle Q, for example, all of the data is entirely off heap. So we tend to have heap sizes of around 2 gigabytes. It's pretty standard for us. So you could run 32-bit, but JVM, but we haven't, for our use case at least, we haven't found that it makes a remarkable difference. But we do find there is a step change between 4 and above, because at 4 it uses untranslated, and then above 4 it has to do a little bit of translation on every memory access because it's a compressed pointer, and that then it there's a small but non-trivial increment in overhead for memory access, but it's not very large. If you're using 64-bit pointers, for example, 64-bit references, that does make a remarkable difference. And if you go over 32 gigabytes, you have to use them, really. And your memory usage goes up, because all the pointers are bigger and you've got so many object references in Java that it really does add up. Your headers are bigger as a result, and your every reference is bigger.
Question here. Yes. So the interesting thing you mentioned about 32-bit versus 64-bit. So I have a question, relating to performance, about the size of the memory that was used, and in one of the talks, that I'd seen earlier, there was the assertion being made, if you just increase the size of your memory, regardless of what your requirements are, you can sometimes actually see a slowdown.
Yes, so
Something- did you-
so the question is, you can see a slowdown if you increase the heap size or increase memory usage in general. Yeah, so you do have some drawbacks. So 64-bit JVMs will use compressed references by default, or they're called compressed pointers. And what that means is if you have a heap of up to 4 gigabytes, it's just 32 bits, and all the top bits are 0. So there's no translation going on. There's no backwards and forwards to try and turn a memory address into just squeeze it into 32-bit. However, above 4 gigabytes, you start to see a bit of a translation overhead, up to 26 gigabytes. So up to 26 gigabytes roughly, depends on the JVM. All it does is multiply by 8. Most chipsets actually do that very efficiently because it's sort of treating it like a long array. So there is support there for shift by 3 bits. Beyond around the 24 to 26 gigabyte threshold, it also has to add an offset because it's not from the start of the memory of the JVM. It's actually a little bit after the start of the JVM that you actually have your heap. So then it has to add another, so it has to multiply by 8 and then add it by a base. Now, all of this is very small changes and very small overhead, but it's on every memory access. So it really does all add up eventually. In reality, if you need that memory, you're better off using it. But if you don't actually need the memory, you're better off using less memory and actually making the heap smaller. And I've found that the 4 to 24 gigabytes is what I traditionally tended to use to make it so it doesn't use the full overhead. And then if you go over 32 gigabytes, it's even worse because you're now using 64-bit references and you've got you've got memory overhead, as well as you haven't got the translation, but you've got the memory overhead. That's even worse.
But it's interesting what you said, and I may not have followed this earlier, is it's as little as 4 gigabytes.
Yes.
So if you don't actually need 8 gigabytes, you might be getting better performance from just 4 gigabytes.
Correct.
And splitting your services into 2 separate containers.
Potentially, or you may find so splitting into 4 gigabytes may give you a slight improvement, but it depends on your use case. Mostly you'll get an improvement if you didn't really need that extra memory. If you actually do need that memory, as in you will see that your performance improves when you increase the heap size. But try heap sizes of just under 4 gigabytes, and you may find that in some cases you can get like a 5% improvement, for example, just by making it smaller, which is not necessarily what you might expect. You can end up then GCing a bit more often if the Eden size then becomes smaller, but that's not necessarily the case. And like I said, in our case, Chronicle uses entirely off heap. We have another data structure called Chronicle Map that's entirely off heap. Once you put all that data off heap, you can actually find that the heap size you need is often around 2 gigabytes. And that will give you often the best performance even for your heap as well.
Question back there.
Yeah, I was curious whether many of the clients are getting timestamps of the file. And also the other question is whether many of them are using Zoom.
Yes. So there's 2 questions. Are our clients getting timestamps off the wire, and are they some of them using Zing? So the first question is, yeah. So the timestamps off the wire is, some of them are doing that, although that's a little less common. But you can, like, there are APIs in some like Solarflare and Equinix, Mellanox to get the timestamp from the message you just received and use that as extra monitoring information about delays. We we tend to encourage looking for outliers. And if you're only looking for outliers, then the absolute timestamps aren't as important. You're looking for variation. You're assuming that your typical latencies are generally good. You want to know how much worse than typical. So your typical becomes your baseline. So you can even compare nanotimes between machines. And obviously the absolute difference between them is random and horrible. But if you look just at the variation of what those differences are, that will tell you how much outlier you're getting, because they're the ones that usually the ones you really care about, not necessarily the absolute difference between them. So, so generally speaking, there's ways around not having really super accurate clocks, because the absolute times aren't as interesting as your variation. So the other question is about Zeng. Yeah, a lot of clients do use Zeng. It's one of our tested platforms. However, in all of these benchmarks, I use Zulu, which is another Azure product. And the reason for that is that Zing has a memory overhead on every access, but it's a trade-off thing. So you get a better profile for GCs, a much better profile for GCs, but you get a little bit of overhead on every memory access. In our case, we tend to write and advocate software that almost produces very little garbage. So then optimizing for the GC doesn't really help so much. Where it does help is if you've got an application where you can't write it from scratch, right? Or such as an application from the third party, or it's in a JVM language like Scala, or it's a legacy application and the exercise of rewriting it's just not worth it. So you may as well throw a Zing at it, for example, and that will often get you not just a performance boost, but it can, in some cases, it avoids outages. So say you've got a cluster of machines, you can actually have outages, perceived outages, just through GC pauses, and that can bring down an entire cluster. And you put Zing in there, and I've seen many cases where they've actually improved service reliability as a result of this. So, so yeah, they definitely, it depends on the client and depends on how much of that code they've written from scratch.
We have time for one more question before we do the raffles for the books and the LJ licenses. So go ahead.
Actually, I have two, but they're quick. In an industry that's so concerned with performance and latency, why do you think a protocol such as Fix, which is really just ASCII tags and values, why has that persisted? And the second question is, you talked about C++ and Rust as alternatives to Java. Have you seen any go?
Yes. So, so the first question was about why do people use Fix? Fix is for better or worse is a standard. That's the thing. It's a standard interchange protocol. There are alternatives to Fix, but they're not widely adopted. They're just not got the traction. Certainly there are elements of Fix protocol that are a real head scratcher in terms of why would you do it that way. And certainly in supporting a Fix engine, you see even worse things such as message types with Unicode characters in them, people wanting to use negative field numbers for some reason, all sorts of bizarre stuff that people want to support. In some ways you're grateful there is at least a standard. How different Fix engines do resend requests is probably a biggest bane. Different exchanges have all sorts of different constraints that you have to comply to. So there's plenty of other things even worse, even in the Fix environment, than the horribleness of the format. It is sort of readable, but this is why we go for YAML, because YAML is actually not so good for a computer to generate something that's somewhat readable, but at least it's somewhat human readable. Whereas Fix is kind of like a worst of both cases, where it's not as efficient as binary, but it's not particularly readable either. But anyway, it's a standard, so it's widely used. So I think that's the reason why it persists. So in terms of other languages, we see a lot of interest in Rust. The biggest problem every one of the clients who are interested in Rust says is finding good experts, and it's really hard. And in general, they're looking to hire one Rust expert. Then none of them are considering even thinking about hiring a team of Rust people. Whereas in Java, you could easily consider hiring a whole team of Rust Java developers with a lot of experience. That's practical. We do see some interest in Go, and we're considering doing a Go implementation, for example, but that one hasn't been as popular so far. We also see like C#, even Ada, which was, I know, low latency Ada. Okay, let's go. But yes, it certainly Rust has got a lot more enthusiasm behind it, particularly in the crypto space. I think it's partly because Rust is used to write some contracts, so it has overlap with other spaces within with the crypto space.
Thank you, Peter. Okay, so now we're going to raffle off some books and the IntelliJ licenses. So I know Gene's not here to run the raffle. So we'll start over there. Mike, you're number 1. We're going to go increment 2, 3, 4, 5. Just remember your number. 6, 7, 8, 9, 10, 11, 12, 13, 14. Chris, you're 15, 16, 17, 18, 19, 20, 21, 22, 23, 23, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. You're 34 standing up. 35. Victor 36, 37, 38, 39, 40, 41, 42, 43, 43 moving. 44. Okay, 44. Wait, great.
All right, so we have three or four JetBrains license. We have 3 DevOps tools for Java developers. 97 things every Java developer, every Java programmer should know, and 1 Head First Java. Get your number, you choose what you want.
Okay, generate.
First number, 39.
Hey, the winner. Okay, congratulations. Yeah, come on up. Come on up. It's your choice. Right?
Your choice. Books or IntelliJ license. One of those books or
I'll take a book, please. No?
yeah, sure.
Yeah.
Okay.
Right.
Thank you so much.
Yeah.
Okay. Next one. Number 2.
Right there. Okay. IntelliJ license.
Okay. I'll get in touch with you in a minute. 1 IntelliJ. 42.
Okay, congratulations. IntelliJ license.
Okay. 2 IntelliJ license. 43.
Wow.
Well, 43 was moving.
Okay. Congratulations.
All right. Don't get 44, please. 4.
Number 4. Hey. Okay. Okay. One of these books or IntelliJ license?
Sure. Thank you. All right, no more head first. Next one. Number 7.
IntelliJ.
Okay, we have 1 more IntelliJ license, then 2 books. 30.
Hey, okay. Okay.
All right, no more IntelliJ license. 4.
Okay, it's a repeat.
That's not so random. Come on.
Okay.
18.
Hey, okay.
What? Thank you.
Okay. The last one.
5.
5. Hey, okay. So pick the winners of the IntelliJ license. If you want to come up here, we'll tell you how to get the license. So
All right.
we'll see you next month for quantum computing and Java.
Their pizza and
Yeah,
there's still pizza
grab
and
some
refreshments,
pizza.
please. Get the pizzas.